All right, Monday. Okay, here we go. All right, so today I have a few cool videos for us to look at before we get back into the material, and one more that we can save until after we're done. And these are designed to help us understand even further, not just interest rates themselves, but really what are they used for, and how are they determined in the real world? That's also a big question. We haven't really raised that issue up to this point, not really. So we'll take a quick peek at that. Although, if you really want to understand more about interest rates, the best place to do that is in an economics class, which you may have already had. But up to this point, we've only been looking at how to use them to calculate the future value of a sum. But at some level, at some point you would like to really ideally understand where interest rates are coming from and what is it that really determines them. That will help with your own personal financial planning. But for right now, what I'd like to do is show you a few videos that will help us understand what we've been doing and give us more of a broad background as to where interest rates come from in the first place. And then we'll carry on with the content in chapter 8. And then I've got one more video that I'll save for the end, which wraps up what we've been doing. So we'll start out with this one that helps us understand a little bit better what compound interest is. Okay, we've been sort of looking at it and understanding it, but I think this will tie it together nicely. This comes from Investopedia, which is a website that you should be familiar with. Anytime you need to know anything about finance or business, the best way to find out about it is at this website called Investopedia. It's kind of like Wikipedia for finance or investments. There's all kinds of great stuff on here. And like right off the bat, how to get COVID-19 student loan relief. Who doesn't want to know about that? Inflation's impact on stock returns, all kinds of great stuff. There's even little courses here that you can follow along for free. But let's say that you decided that you wanted to know more about interest rates. You go to Investopedia and say, oh, Investopedia, tell me more about interest rates. And it'll come up with all kinds of these excellent articles that you can read, and that will help you understand more about what we're doing here. For example, how interest rates affect the US markets. That's an important detail. Okay, now again, like I said before, this is something you'd normally study in an economics class rather than a math class, but at some point it will be interesting and useful to you to have a better feel for how interest rates affect the economy. Because if they affect the economy, that means they're affecting your investments, which one of these days you will actually have investments. I know it's hard to believe now, but one day you'll have enough money to invest. And when you do, you need to decide what to buy. And one of the decisions, or one of the factors that goes into your decision-making process, is what do I expect to happen to interest rates? And how will that affect my stocks and my bonds? Whatever else I've chosen to invest in. So all of these articles will come in very, very handy towards that goal. So we're going to start with this one, which is specifically, though, about compound interest. Okay, we've been studying compound interest, but I think it's always good to have more background information about it because it is a fairly complex topic. All right, so why don't I send you the link and we will get started. All right, there it is. Let's pop that up there and let's start. Hmm. It was, wasn't it? Ah, interesting. Yes. But it ties together what we've been doing. And you can see that when you earn interest, there's two types going on, typically simple and compound. And of course, the compound interest is a fairly small percentage of the total in the early years, but it does grow very quickly compared to simple interest. And if you leave the money there long enough, eventually you'll reach a point where you actually have more compound interest than simple interest, although that takes a very long period of time. Now, so compound interest is actually helpful to savers, but it also makes borrowing more expensive when you go to borrow money for, let's say, a car or a house. So it helps and it hurts. It helps the lender, it hurts the borrower. So we need to be able in our positions to understand how it works. In other words, if you do decide to buy a car or to buy a house, you have to know exactly how much it's going to cost you. That's the only way to make the right decision. You have to know exactly what this is going to entail before you decide if it's worth your while to borrow the money or not. Um, anyway, so that was fairly short, but it was very concise, very helpful. And you can see what I mean about Investopedia. They do have a knack for explaining financial principles in a very straightforward way. They're trying very, very hard to avoid overwhelming you with technical details. And so you'll find if you read the articles on their website, it's pretty much the same thing. They're trying very hard to keep it at a level that people can understand, even if they don't have any real finance or economics background. Okay, because let's face it, that is the case for many people. A large percentage of people don't really have much background. And so how do they invest their money? Well, websites like Investopedia are certainly very helpful because obviously you don't want to invest your money unless you really understand what you're doing. All right, well, anyway, let's check out now. Here's another one. This is more about interest rates themselves. This is more big picture stuff. Where are interest rates actually coming from? So let me send you this one now. Oops. Uh-oh, what happened? I think I hit the wrong button. Yeah, all right. Yes, I did. All right, we're back. Hold on. So let me send this off to you in the chat room. So this one is Interest Rates by Wall Street Survivor. And let's see what they've got to say for themselves. All right, let's check it out. right, are we done? Okay, so that wasn't really the big picture one. I thought it was. The next one is the big picture one, but it's kind of funny how they ended up choosing the exact same numerical example in both cases. I guess it's just easy to follow those particular numbers. They're nice round numbers, $10,000, 5%. And so you can see exactly how your money grows when you're saving. But of course, if you're borrowing, it can really pile up, can it? So that was a very good example of, you know, the same individual is both borrowing and lending. And this will often be the case. Most people have some savings and some investments, but yet they may need to borrow money to buy a car or a house. Items that are so expensive that you can't realistically just pay for them yourself, and yet you can't really wait realistically to save up enough money to buy a car before you get one, because you do have to go to school and you do have to go to work. So for the most part, people finance cars and houses with loans. But also, it's not just those. Any large ticket items that you might need for your home, like furniture and appliances and things like that, are often financed with borrowing. And so it becomes extremely important to understand how the interest rates are being calculated. All right, now the next one, I'm pretty sure, is more big picture stuff. I remember when I looked at it the other day, it says here it's called How Our Interest Rates Are Determined. This should be the one that actually explains to us what factors in the market are actually determining the level of interest rates that we're looking at. This is, again, something that we don't really need for this class, but I think it's important for you to understand what's going on in the economy to make better decisions about how to invest your money. So let's take a look at this. And again, if you're interested in learning more about this, you can go to Investopedia. And also, you might do something really interesting, and that's take an economics course in the economics department. Especially macroeconomics is more focused on interest rates than micro would be. But everything you do in both of those classes is very interesting and useful. So, something to think about. You might have some free electives available to you, and you might want to think about moving over there and checking this out. But anyway, here we go. Let's fire this over there and let's take a look. All right, I guess we're all done. All right, well, that was pretty interesting. Now, you've probably heard of the Fed before, although maybe you never really knew what it was. The Fed, as they mentioned in the video, is short for the Federal Reserve System, which is what is called the central bank of the United States. And what that really means is that they are the ones who oversee the banking system, but they also are the ones who ultimately determine the level of interest rates in the economy. And their goal, as they said in the video, is to make sure that we have the best of both worlds, which is to say low inflation and low unemployment, which is not easy to do. There's a tendency for them to go in opposite directions. In other words, when inflation is high and unemployment tends to fall and vice versa. So, but neither one is good. Obviously means people are out of work. We don't want that. Inflation means prices are rising, and we don't want that either. So the Fed has a tough job to do. And they've done a pretty good job since they were created in 1913. But, you know, when you hear about the Fed in the news, it's because they're possibly taking steps to either raise rates or lower rates. And anything they do will have a major impact on the economy. So there's a lot of discussion about the Fed in the financial press, like the Wall Street Journal, for example, constantly has articles about what the Fed is doing. And they're trying to help us understand what the impact would be if the Fed does decide to change the level of interest rates. So that's more big picture stuff. We're trying to help ourselves understand at some level what exactly is it that causes rates to rise and fall, and why is this happening. But ultimately in this class, what we're trying to do is understand how they affect the cost of borrowing and the rate of return to investing our money. So it's all very interesting. It all ties together very nicely. But anyway, right now, we want to get back to the material, the new content. And you can see I've scrolled ahead in chapter 8 to this slide called annuities. Now, if you look at this word annuities, you'll notice something interesting. Hiding in this word is the word annual. In other words, the words annual and annuities are both taken from the same Latin word annum, which means yearly, basically. So basically in finance, we have a structure called an annuity, which is a repeated series of payments that occur once a year and are equal to each other. So some financial assets do make cash flows that are could be considered a type of annuity, and some types of loans are structured as a type of annuity. And so that's why it's important to understand how annuities work. And of course, we will at some point develop a formula to help us understand how annuities determine either the amount of money we'll have in the future or how much we will pay to borrow money. So let me just give you a quick example of this. It turns out that in many states, virtually every state, as far as I know, every state has a lottery of some kind. It helps them raise lots of money, but in many states, large lottery prizes are not distributed as a single payment, but as an annuity. Okay, for example, if a prize winner wins a prize of $1 million, the state may pay the money at as an annuity of $100,000 per year for 10 years. Okay. Now, when you buy a ticket, all these details have to be written on there somewhere. In other words, this is not just something that they can decide at the last minute. They will have decided in advance that when your prize reaches a certain point, that instead of handing it to you all in one check, they will split it up into equal pieces. Partially, they do this to save money, but partially, they've found from experience that a lot of lottery winners who have these big prizes end up spending it all almost immediately, and they end up losing. In fact, a lot of them end up in debt because they've suddenly, for the first time in their lives, they have all this money available to them and they really don't know how to handle it. So part of the reason for this is to help basically people avoid spending it all right away, but also it does save the state money as well. So, but they have to tell you this. I mean, if you are buying a ticket in a lottery like this, they have to let you know what level the prize has to reach before it becomes an annuity. But you can see here that they're actually paying you $1 million, 100,000 a year for 10 years. Now, here's the thing though. If you had a choice, which would you take? $1 million all at once or $100,000 spread out over 10 years? Which one would you rather have? Now, let's just imagine that you have a lot of self-discipline and you will not spend all the money right away. In fact, you already have plenty of money and your plan is to invest this money for your retirement. Which of these two choices would be better? $1 million up front or 100,000 for 10 years? In fact, I'll tell you what, why don't we turn this one into a poll? I think this is a perfect poll. Now, keep in mind, this is based on the assumption that you're planning on investing this money, not because you want to buy a Ferrari or something. What the hell is going on here? The poll thing doesn't seem to want to work today. What's going on here? Usually when I say edit, there you go. What was that all about? Why did it keep? Okay. Here we go. So if you are planning on investing your winnings, which of the following would make you better off? Okay. $1 million today or 100,000 per year for 10 years. All right, let's find out what everybody thinks. Okay, well, no, a few more people are voting. All right, I think everyone who wanted to vote has voted. Well, I'll tell you what, it turns out, to our surprise, it turns out that in terms of just an investment, you actually would be better off having the $1 million right now. And the reason for that is because you would have more time to earn interest. And we're going to see that in our examples. Okay, so the correct answer turns out to be $1 million today. All right, so if you had a choice, if they said to you, listen, which one do you want? You would have to consult with a financial planner before you make a decision like that, because it's not always intuitively clear what would be the correct decision. So here we're getting 100,000 for 10 years. So in terms of investments, the money, the future value of $1 million today is greater than the future value of 100,000 per year for 10 years. Now we can't prove it just yet, but we will. By the time we're done with this discussion, we will be able to prove this. Okay. In fact, we'll do this at the end. I'll show you how much of a difference it makes. So $1 million today versus $100,000 per year for 10 years. But, when you bought the lottery ticket, presumably you knew that this is what was going to happen if you won the big prize. So you don't really have any, and of course, nobody's going to complain about this. It's still a lot of money. It's just that you would have been better off having the $1 million right away. Now, having said that, we'll see later on too, some states will actually tell you, listen, we'll give you the following options. Instead of 100 grand per year for 10 years, why don't we offer to give you, let's say, $700,000 right now? In a case like that, the decision will depend, which one is better off, the decision will depend on what the level of interest rates is. That kind of decision would be, you could not make it unless you knew what interest rates were like today. So that example we'll save for later on. But right here, it's clear that the $1 million today would be worth more than 100,000 per year for 10 years. Now, how do we know this? We're going to find out by introducing another formula, which is not terribly different than the one we've been looking at. This other one, we've used it so many times in our examples. Let's go back and get this one. Actually, I want to have it here available so I can show you. When I introduce the new formula, we want to be able to see how the new one is different. So we're about to introduce a formula that lets us calculate the future value of an annuity. All right, so now, by the way, before we go any further, I want to mention one thing though. And this is something that you see in financial literature. It turns out that even though an annuity technically only refers to annual payments, there are many cases where the payments are made more frequently, such as monthly. For example, the payments on a car loan occur every month, and each payment is the same amount. In this case, we can think of the monthly payments as a monthly annuity. All right, so even though you're technically misusing the word annuity by calling it that, this happens all the time in finance, especially monthly. Many loans, you may already know, if any of you has ever actually bought a car, for example, it's possible. You only have to be 18 to borrow money. But if you have borrowed money to buy a car loan from a bank typically requires monthly payments. And everyone is the same. That's how it's normally structured. So whatever amount you have to pay, normally they structure it so that every monthly payment is exactly the same. And the same thing is true for a house. The payments are made every month, and each one is exactly the same. So we might think of this as a monthly annuity. And so because it is not technically an annuity, but we can think of it as a monthly annuity, and because of that, we can use the same formula whether the payments occur every year or every month, just by making the necessary adjustments. All right, so I just want to mention that right up front. The formula we're about to show you can be used for annual payments, semi-annual payments, quarterly payments, monthly payments, you name it. It applies to all of them. Okay, even though technically the word annuity should only be used for annual payments. Instead, though, we often see it used for more frequent payments by calling it a quarterly annuity or a monthly annuity or whatever it happens to be. The logic is exactly the same. All right, so finally, with all that being said, let's take a look at this new formula. Now, because this one involves a repeated series of payments, which we did not have before, of necessity, the formula is more complicated than what we had earlier. It's not much more complicated, but it is more complicated. So let's be aware of this. All right, are you ready? So remember, this is our old friend, the future value of a lump sum of money. This P, or principal, occurs once, and that's it. In the next formula, we're going to replace the P with something else, which refers to the regular payments or repeated payments. Okay, so here it is. Now, let me go grab this one back so we can see them side by side. And so you can see the differences. All right, now there's not a whole lot of differences, really, as far as the symbols are concerned. The P or principal for lump sum has been replaced with R, which stands for repeated payment. And this formula on the left refers to annuities. The one on the right is for lump sums, a single payment, that is. Other than that, the differences are pretty small. I think you'll agree. Okay, so it is scary, but you know what? Given all the practice we have with the one on the right, the one on the left is really just a tiny bit more complicated. We just have to be extra careful with our parentheses. On the right, we were extra careful. On the left, we are going to be extra careful. Okay, so yes, we are, but as long as we're careful, there's no reason why we should have any problem with this brand new formula, which, like you said, is pretty frightening looking. But you know what? So was this one too when we first saw it, wasn't it? It's not frightening now, is it? No, in fact, it's kind of easy. So the same thing will happen here after you've done enough of them. You'll start to say, you know, this isn't so bad. Yes, you will. It's hard to imagine now, but yes, you will. Now let's see an example of this. All right, are we ready to dive into one? So this one we'll work on it together, and then we'll do some more examples where you get to do some practicing. Like here, for example, the winner of a lottery will receive $5,000 semi-annually for 5 years, starting next year. The funds will be invested in a bank account that pays an annual percentage rate of 6%, compounded semi-annually. How much will the winner have in 5 years? Now, let's pick this apart a little bit and see what's going on here. This means, the way it's written, that you'll get, instead of $5,000 once a year or every month, you'll be getting these payments twice a year. Okay, so for 5 years, in fact, if you were to draw a timeline for this, here's today, 0. In 6 months, you'll get $5,000. In 1 year, you'll get $5,000. In 18 months, $5,000. 2 years, $5,000. And this will carry on until we get to year 10, which case we get another $5,000. So how much are they actually paying us? There's 10 payments of $5,000 each. So in other words, if you actually just put this money, let's say that for whatever bizarre reason, you decided to take this money as cash and just throw it into the drawer in your bedroom. At the end of the 10 years, you would have $50,000. But because we're putting it in the bank, presumably we'll have more than $50,000 at the end of the 10 years. The question is how much. Now, the interest is 6%. So by the way, in our formula, this is what we mean by R. Capital R from now on will represent the repeated payment, which is, oh, sorry, I got the wrong thing here. It's not 50, it's 5. We're getting 5,000 every period. And instead, what we're going to call these is semi-annual periods. All right. If these were quarterly payments, then they'd be quarters. If they were monthly, they'd be a month. Instead, what we have here is semi-annual periods. Now, the interest rate is 6% per year. But if you recall, N in our formula is the compounding frequency, which in this case is twice a year. All right. So in other words, it's telling us that the rate is compounded semi-annually, twice a year. So you're basically getting 3% twice a year instead of 6% once a year. And then T, the time element is still, any way you look at it, 10 years. Wait, sorry, no, 5 years. My mistake. It's 5 years because it's 10 periods. 5 years. So what else do we need? We need capital R, lowercase r, N, and T. No, that's it. We're done. Now we can plug these in to that scary looking formula and come up with our future value. All right, let's see how that works. And then what I think we should do is develop a strategy for figuring this out with our calculators, okay? Because this is going to be the challenge. All right, so that's the formula. Now remember, we're getting $5,000 twice a year. So R is the repeated payment. The annual rate of interest is 6% per year. N is the compounding frequency. And of course, T is 5 for 5 years. Now, you can see that clearly the numbers have been plugged in correctly. But what should we do to make this easier to solve for? Well, let's see. How about if we do this? Here we have 1 plus, this is 3%. So what we actually have here is 1.03 raised to the 10th power minus 1, all divided by 0.03. Now that is easier, but we still have to figure out how to actually implement it on that calculator. So let's try that right now. Let me just copy this here, and let's see if we can figure out a strategy for making this as painless as possible. So I think the way to go is this. And you can, disagree and do something else, but I think what you should probably do, hold on 1 second, is start with the 1.03 to the 10th power. 1.03 exponent 10 equals. So if you do that first, all right, so I got my calculator out right now. I'm going to confirm this. 1.03 to the 10th. Equals. So you'll have a number like 1.343 something. From that, you can subtract the 1. Okay, so subtract the 1 equals, and you'll have a fraction now, which you can then multiply by 5,000. And by doing this, you notice I'm actually going in the numerator from left to right. I'm solving for what's in the brackets. This equals approximately 0.34. Times 5,000 gives us approximately, wait, hold on, I screwed it up somewhere. 1.03 raised to the 10th equals -1 equals times 5,000. That's about 19.58. And now the last step is divided by 0.03 equals, and that's where you're getting your 57,319. And here you can round it to either 39 cents or 40 cents. Okay, so what I'd like you to do is take out your calculator and make sure that when you follow these steps, you're getting exactly what I just got. If not, well, we'll keep going, we'll keep practicing. And when you get it straight, what I'm going to do is show you another example, and then we're going to practice this for a while, because this is the only way this is going to work. You've got to practice it. All right, did everyone get that? All right. Okay, good. All right, everyone else? All right, so in about a minute, when I'm sure everyone else is ready, we'll start another example. All right, so let's try another one. These don't have to be lotteries, by the way. This could be anything. All right, let's try this one. But it could be a lottery. Suppose, I'll tell you, I'll give you a simple one first. Suppose that a lottery winner is scheduled to receive a prize of, in fact, why don't we look at the one we had before? 100,000 per year for 10 years. By the way, I do want to mention here that normally these types of annuities, the payments do not typically start immediately. They typically start in 1 year. If not, we have to adjust the formula. So we'll just assume from now on the payments start 1 year in the future, or one period. Okay, the payments are made annually. The rate of interest is, let's say, 6% per year. Okay. How much? Now, assuming, now you notice too, we're assuming that the winner invests the entire how much will he or she have in 10 years at the end of the, okay, after all the payments have been made. Okay, so in other words, what's happening here is that well, first let me grab the formula back for you. Just for reference, okay, so what do we know? It's a 10-year annuity. The payments are $100,000 per year. We're keeping it simple by assuming annual compounding and annual payments, and the rate of interest is 6%. All right, so given the formula, why don't you try, now again, this is fairly simple. Whenever n is 1, that really simplifies things quite a bit. Why don't you try to figure out how much money this person will have at the end of those 10 years? So this is that $1 million lottery, which they are only getting $100,000 per year for 10 years, but they're investing all of it at a rate of 6%. How much will they end up with at the end of those 10 years? All right, so what you're going to do is plug in the numbers and then do the algebra on your calculator and see what you come up with. And here's a hint. The total payments will be worth $1 million. So your answer has to be more than $1 million. Oh, we have an answer. Oh, that was fast. Is it $1,318,079.49 or 50 cents? Yes, it is. My God, that was fast. Oh my God, you see, this formula isn't that scary after all, is it? So how did you get that? Well, 100,000. Then we have 1 plus 0.06 over 1. The exponent is 1 times 10 minus 1 all over 0.06 over 1. So inside here, you actually have 1.06 to the 10th power minus 1 all over 0.06. So what you can do now is take this. Let me just write this down one more time. So we have room So what I think you might want to do is solve for what's inside the brackets first. 1.06 to the 10th equals -1 equals. So now you have what's in the brackets times 100,000 equals. That gives you the numerator, and then divided by 0.06 equals. Now what I'm going to do is get out my calculator and show you what you would get after each of those stages. 1.06 raised to the 10th equals -1 equals. So in the numerator, you have this enormously long number. It's approximately 0.7908, which when multiplied by 100,000 is about 79,084, let's say 0.77. And then when you divide by 0.06, that gives you your final answer, which is 1,318,079.49. And that's your final answer. So this very smart saver was able to accumulate $1.3 million by just not spending all the lottery money, which is very unusual apparently, but it can be done. All right. So I guess we can try another one. There's nothing like practice. As you probably already know, especially those of you who are, let's say, musicians or painters or poets or whatever you're studying, you all know that practice is what makes perfect. Dancers, that's right. I always have a lot of dancers in my classes. You can't be a dancer without practicing, can you? No, 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 no. All right. So anyway, let's try this one. An investor decides to put $1,000 per month. Now, this is not a lottery prize. This is an individual who's saving money, decides to put $100,000, let's say every quarter, into a bank account that pays 4% interest, but compounded quarterly for the next 20 years. How much will the investor have at the end of this period of this time? All right, so let's just see what variables we have here. So the repeated value is the $1,000. Now, the time is actually 20 years. N is 4 for quarterly. So if you notice, the frequency of the investing equals the frequency of the interest payments, which is 4 times a year. And what else? And the rate of interest is 4%. So the question is, how much will this person have at the end of that period? Well, it'll be a lot of money, but the question is how much. So let me remind you what the formula is. That's our formula. You have everything you need, 1,000. All right, so once you take a minute, now I can tell some of you will have this very quickly. That's good. That's impressive, actually. You're very good with your calculator. That's what we'd like to see. All right, so once you figure out how much money, and by the way, before you do something like this, just try to visualize how much money this person will have if there's no interest. $1,000 4 times a year for 20 years is $80,000. So your answer has to be at least $80,000. All right. So I'm going to quickly just pencil in all the actual numbers that you'll be using. All right, so now your job is to simplify that and then throw it into the calculator. Okay, we have some 121,671.52. Perfect. Exactly. We've got some real speedy calculators in here. Wow, I'm impressed because those are not simple formulas. All right, well, let's see why this is true. All right, so I'll just copy this again. So this one could be simplified as 1.01 to the 80th power minus 1 all over 0.01. So you could put 1.01 raised to the 80th power equals, don't forget the equals, minus 1 equals. That'll give you the numerator, what's in the brackets. Then you can multiply that by 1,000 to get the entire numerator. And then you can figure out the denominator. So I kind of like breaking it up into these 3 steps. So in the numerator, in the brackets, 1.01 raised to the 80th power minus 1 is 1.26, approximately 216 71, let's say 5 2. Multiplying that by 1,000 gives us 1216.7152. And then when I divide that by 0.01, I should get my final result, which you will round to dollars and cents, 121,671.52. Okay. And so that's how we got it. Man, interesting stuff. All right. Now, I'll tell you what, we're going to do something slightly different here. These formulas, so far up to this point, we've been showing only examples where we save our money What about borrowing? Well, we can use these formulas for that too. What I'd like to do is show you an interesting application of this. If you look at it carefully, if you are borrowing money, this R actually becomes the payment on the repeated payment on your loan. So imagine this is a mortgage, which is a series of monthly payments that are used to buy a house. What if I wanted to know if I could afford to buy a house by figuring out what the monthly payments are? I could take this formula and rearrange it algebraically and solve for R. And that would give me a very useful result. And so if I did that, I'd end up with this, which, as you can see, is simply an algebraic rearrangement of that same formula. And in fact, in a lot of cases, if you're trying to make a decision as to whether or not you can afford to buy a house or a car or whatever, often the decision comes down to the monthly payments. All right. So in other words, if you can afford to spend $600 a month on a car, well, that's a lot of money for a car. But if you can, then that means that you have to know how much the monthly payments are before you sign on the dotted line. All right. The sticker price is important, but it's hard to visualize. Let's say you go to this dealer and the car you want is $30,000. You say, well, that sounds like a lot of money, but can I really afford it? And they say, well, the monthly payment is only $550. And you say, oh, that's good because I can afford 600. Therefore, you can buy the car. And that's really the bottom line when you buy such expensive items, is the size of the monthly payments. So this is an extremely useful formula to have in your back pocket. Now, this example that's in the slides is a little different because this is an investor who's saving, but the target is $100,000 in 3 years. So the goal here is to figure out how much must be put aside every year in order to reach this goal. So what we're going to do is set up this formula with the following information. Now, for the first time, we'll actually be given the value of A. That's normally what we're solving for. We're assuming that this investor can earn 3% per year compounded annually. And this is a 3-year investment. So what we'd like to do is figure out how much this person must put in the bank every year in order to reach that target of $100,000 in 3 years. So let me show you how this is done. Now, here you just plug in the numbers, but what I'd like to do is take this and simplify it a little so we can see how to use it on the calculator. This is actually the equivalent of 100,000 times 0.03 divided by 1.03 to the third power minus 1. In fact, what I can do is simplify the numerator even further. Okay, now what do we do with this one? Here's a possibility. 3,000. Now this one involves parentheses, by the way. Let's try this. 2 parentheses, 1.03 raised to the third. Let me double check this on my calculator, make sure that I'm not messing this thing up. Because like I've said many times before, every calculator is a little bit different. And so I want to make sure that what I'm doing works on this one. All right. Hold on one second. I have to. I'm double checking one more thing. Oh, I knew I messed it up. Hold on. I missed one of the parentheses. There should be a 3. Sorry, parenthesis after this 3. And then an equal sign. There we go. And so you'll get 332, 353.04. Well, that's a little messy, isn't it? Yes, but it works. Man, the trick is that you've got 2 consecutive parentheses here. And then, by the way, here's a helpful hint with these formulas. For every left parenthesis, there has to be a right parenthesis. So you notice how there's 2 here on the left, and then here's 1 and 2 on the right. Eventually, for every parenthesis on the left, we need to have the exact same number on the right. Okay, 1 on the left, 1 on the right. They have to match each other or balance each other. If you don't have the right number, you will get the wrong answer. So, did everybody get the correct answer? Oh, good. All right. So yes, I see that the formula is getting a little bit out of hand, but I don't see any reason why we can't do this. But I also think we need more practice. All right. So let's try a slightly different one here. Oh no, not yet. Not yet. We got 20 minutes to go. All right, I'll tell you what, let's try this one. Okay, you'll see. It'll work. And don't worry, we'll get plenty more practice. We're not just going to leave this topic right here. We'll come back on Thursday and get more practice with these because, like I said, these do require a lot of practice. But once we're done, we're done. I mean, there's a certain point you'll reach where suddenly you're not just throwing in numbers, you actually understand what we're doing. And once you reach that point, then you'll never, ever have a problem with it again. It's that at first you're just sort of trying it and you're doing it and you're working with it. But at some point it starts to suddenly click. And then you'll say, oh, I can see what you're doing. No problem. All right, so let's try a different one. How about this? Oh, wait a minute. You know, I just realized I've gone out of order here. But that's okay. There's another topic we have to cover in this chapter that actually, now that I'm thinking about it, this probably worked out better. The topic that I want to save for last is explains to us the connection between 2 different ways of quoting interest rates. You know what? I think I'll save that one for next time. And we also have a video for it. But right now, I think this worked out better because this formula that we're seeing here is very closely related to what we were just doing last time. In other words, our future value. Yeah. All right. So we'll carry on with this. And then, but the next time, we're going to go to a different topic. Yeah. Yeah. So I accidentally changed the sequencing a little, but that's okay. We're going to cut back. If you look in your slides, you'll see that there's one more topic called effective rate of interest, which we'll save that for next time. Let me just do one more example here. Suppose, okay, another example. Suppose, okay, hold on one second. I have to plan this on my calculator. Let me, so that I want to make sure that it works out just fine. All right, hold on a second. All right, I'll be with you one second. I'm working on an example here that I want it to work out very nicely. Okay, so okay, I've got one. Here we go. So let's just say that I don't know. How about Bill Jones wants to buy a $40,000 car and can borrow from a bank. Can borrow this from a bank. Okay, the bank requires monthly payments over a period of 6 years. The bank charges 6% interest compounded monthly. What will be the size of Bill's monthly payments? There we go. All right. So this is a perfect example of what we're doing right here. So if you look at this formula, let me grab a copy of the formula. We know that A is 40,000 because this is the amount he's borrowing. In other words, that's the $40,000. And R is 6. And N is 12. And T is 6. All right. So why don't you give that a shot? So in other words, what you're actually doing here is this. There we go. Now, it's a bit of a mess now. So what you should probably do is simplify it as much as possible and then use the approach we had before with the double parentheses. All right. Let me, in fact, why don't I put this somewhere so you can see it's not the same numbers, but let's see what I can do here. Just so you remember how this was approached last time. We took 3,000 and divided by all of this. And at the end, we subtract, we just had an equal sign. And so using a similar approach right here, but changing the numbers, of course, give this one a shot. So first simplify everything, and then try to squeeze it into a formula just like this one. Oh, we got somebody. 469, let's see, 462.92. Yes, that's it. So let's see how that happened. All right, let's move on to the next slide. So first of all, our goal is to simplify it. Does it ever need to be simplified? Let me tell you. Okay, so in the numerator, we have 40,000 times 6% over 12 is actually 0.005. And that numerator actually reduces to 200. So let's try this approach. 200 divided by double parentheses 1.005 exponent 72 close parentheses minus 1 close equals. That should do it. Try that and see what happens. Yep. So it's 462. And the penny, it's 9155 or something. So let's round it to 92. All right, does that work for everyone? Good, beautiful. All right, so I think we don't really have time to do any more of these, and plus everyone's getting a little worn out, I think. So in the middle, now I did realize only afterwards that I went out of order slightly. The next and final topic in this chapter is something called effective versus annual rate of interest. So that's a fairly quick topic. We'll pick that one off next time. And then we also have a short video to go with that one. So we'll save that for Thursday. But in the meantime, when we do come back, I also want to get a lot more practice with these, especially these annuities, because they are kind of difficult. So but like I said, after you've done enough of them, you'll discover pretty quickly that they're really not that difficult. I mean, yes, your calculator skills are being stretched out a bit, but you know what? I mean, let's face it, whatever discipline you're in now, the work you're doing is more advanced than it was last year, isn't it? Yes, it is. So it's the same idea. You need to stretch your skills a little bit by learning more and more how to do these very complicated formulas on the calculator. And again, this is the kind of thing you'll need to know in the future when it comes time to buy that first car of your own. So, all right. So I guess we'll knock it off right here. And then between now and then, really all you should do is just make sure you understand what we've been doing. And we'll just carry on from there on Thursday. Okay. How does that sound? Are you too stunned to carry on? All right, good. So I'll see you all on Thursday then.
Bye, Professor. Have a nice week.
All right, you too.
Thank you.
Bye.
Bye.